Edo-Arctic 2, Polar Research for Education, innovative program in Poland and Norway. Webinars.
They were going to talk about ocean currents, and this lesson, this webinar, just as all the other webinars that we conduct in the framework of Edo-Arctic 2 project, is accompanying, or maybe treated as a wrap-up or as an introduction, as an intro to our educational toolkit, which is also dedicated to the same topic. And there are more educational toolkits, both in English and Polish. Some are also in Norwegian that are focused on Arctic issues and Arctic problems in general, quite often in the context of climate change. And this will also be the case today, because ocean currents are very much affected. It's the system that's very much affected by the current climate change, but also they are a very important part of the whole climate system. They contribute significantly to the systems. We will learn how. So, ocean currents and climate. First, let's start with oceans in general. So we have one ocean, the so-called world ocean, and it was decided to divide the ocean. I mean, they are, of course, they are different, but they form the world ocean as a whole. But they can be divided into some smaller bodies of water, which are oceans, and the boundaries of them are rather conventional. So if we look at the map, we could try and divide them differently, but this is what was decided, that they should be named this way and the boundaries should be here and here. So we have 5 oceans, and there used to be 4 formally recognized. I remember that I was at school. I was taught that there are 4 oceans, namely Pacific Ocean, which is located between North and South America, Antarctica, Australia, and Asia. And there is also Atlantic Ocean, which lies between Europe, Africa, Antarctica, and North and South America. Indian Ocean, which lies between Africa, Asia, Australia, and Antarctica. And Arctic Ocean, which is of our particular interest, and which lies between the northern shores of Europe, Asia, and North America. But actually, now we have the 5th one, and it's the youngest. It doesn't mean that it was formed. It was formed later than other oceans, or recognized or discovered. No, it just was. Its boundaries were recognized not that long ago, actually. So Arctic Ocean is the smallest one of all, and also the shallowest one of all. So the South Ocean can be also called Antarctic Ocean. And all the oceans, but also all the seas on our planet, form this one big world ocean. And the world ocean takes much of our surface. I mean, the surface of the planet. It constitutes as much as 71% of total surface of the Earth. So it's quite a lot. It's more than 350 million square kilometers. And when we look at the map, which we'll do in a second, the oceans and the seas are characterized by not even distribution around the globe. This means that we have more ocean in the south. In the northern hemisphere, there's around 39% of land, and the rest is covered by water, covered by ocean. And in the southern hemisphere, there is much more surface covered by ocean. 89% is covered by ocean, and only 80% is land, which also influences our culture, where the civilizations developed, and or the other implications of that fact, historical implications mainly, but also it influences the way that the system of ocean currents is formed. So finally, this is the map. Here we have the Southern Ocean, Antarctic Ocean, which is stretching from the Antarctic coast to this, maybe this 60 degrees south. And it joins the Pacific, Atlantic, and Indian oceans. I mentioned that the Southern Oceans is the fourth large. I mentioned it was the youngest. It was formally approved as a separate body of water by International Hydrographic Organization in the year 2000, and also it's the fourth largest of all five. So it's not that large in comparison with other oceans. So if we talk about ocean currents, it means that in general we recognize the dynamics of the ocean. We recognize that they're not that stable. No, maybe they're not that passive. We would rather say they're not that boring. They're not that dull. It's not like a bowl of soup. And there are lots of movements going on in the ocean, in the world ocean, and they're very intense, and they have different grounds, and they can be categorized as waves, tides, and currents in general. So currents, which are our main focus today, are like rivers in the oceans, like a river flow. So they have a direction, they have a rather regular volume of water, and like a rather definite path. So they look like, or they act as cohesive streams. We can further divide currents according to many criteria. For example, we have horizontal and vertical currents, but actually it's not the most important categories and division that we should focus on. So I mentioned that oceans and world ocean are not like a boring bowl of soup, and not only because there is also movement going on, but also all water reservoirs consist of layers, and the layers are determined mainly by temperature. So we have the top layer of the surface, and it's called often the epipelagic zone, and sometimes it's called an ocean skin or sunlight zone. So this is where the sunlight is available, which has further implications for life, especially, and vegetation in this zone, in this layer. So this layer interacts with the wind, and there are waves that mix the water and also distribute the heat. At the base of this layer, there's a thermocline, and thermocline is like a transition layer between warmer mixed water here at the surface and cooler deep water below. And it's quite easy to tell when you have reached the thermocline in a body of water. Of course, thermoclines occur at different depths, but if you ever if you're ever at the ocean or at the seaside and you're going swimming, and many of you may have encountered thermoclines because it's like a sudden temperature change, sudden temperature drop. So the temperature drops sharply from the temperature here of the mixed layer to a much lower temperature of a deep water. So, like I said, the depth, also the strength of the thermocline varies with the seasons, from season to season, for example. And for example, in the tropics, it's rather persistent. It's rather variable in temperate regions, and it's shallow or even non-existent in polar regions, where the water column can be very cold from surface to bottom. And also it has other implications, because that means when there is no thermocline, or where thermocline is rather weak, there is a lot of mixing. So these layers are very important for example, for life in the oceans, and also for ocean dynamics. So what we see here are further consequences of those layers, and the system of layers, or the fact that water is layered, is so-called stratification. So when the ocean is heating, when the temperature is growing, the stratification that is stronger. That means that that the layers are more pronounced, say. So even though the ocean water circulates around the globe, which we'll see in a minute, it is rather difficult for the water to wander into the depths, like I said, the thermocline. Actually, there are only a few places on Earth where water can freely cross this border, and deliver, for example, oxygen to the bottom of the ocean, because if there is no mixing, there is no or little oxygen at the bottom. If it wasn't for those few points, that we would say those pumping stations for the ocean, Earth's ocean would just turn into complete deserts in terms of life. They would be biological deserts. And also the oceans today are fairly evenly saturated with oxygen. So there's a little more of oxygen in cold fresh water, a little less in the water that has been in the depths without light hundreds of years, for example. So this is the situation with layering. So when I mentioned that when the ocean temperature is growing, the stratification gets stronger, and the water does not sink deeper. And there is not only disturbance of circulation in the oceans, but also those pumping stations, those very few pumping stations delivering oxygen to the bottom, don't work. So we have a reduction of oxygen supply to the depths, and when we have not enough Oxygen, it means we have anoxia or hypoxia. And as everything in our geosystem, it might change, or it already changes, the biogeochemical cycles on Earth. And those cycles are very important for the balance of species. So when such events occur, the species composition is disrupted. And not only the species composition, but also the whole climate system. So there are serious disturbances when the temperatures on Earth reach very, very high values. It's like a thermal shock. And has it ever occurred before? Yes, of course. And because temperatures on Earth were much higher than today, and it doesn't mean that we do not affect the climate change or do not cause the climate change now. It just means that the temperature was much, much higher. It also means that the conditions on Earth were not favorable to us, or wouldn't have been favorable to us because it was a long time ago and long before the humans even appeared on Earth. So, like I said, it was a thermal shock, and so strong that, according to some hypotheses, it could stop circulation in the ocean and also lead to extinction of marine organisms. So it's a warning to us. So for now, we shouldn't be that worried about it, that all the species in the ocean would go extinct, because we still live in a fairly cool environment in comparison with Paleozoic, Mesozoic, or Cenozoic eras, but geological eras. But the temperature is still rising and has been rising for several decades, and it might mean that there will be problems in the future. But fortunately, we still have, for now, polar zones. They receive much less heat from the sun than, for example, around the equator. So the water is colder, the water is denser, and these are pumping stations for the oxygen. So these are the regions which are crucial for many other reasons, but also for this reason that these are the places where the thermocline is weak or not existent, and there's a lot of mixing, so the pumping stations for the bottom of the ocean. Okay, so what actually happens inside the ocean? So like I said, like repeated several times, I believe this is not a monotonous bowl of soup. And this image actually represents the system of currents during winter in northern hemisphere. So blue are cold currents, which means they're colder than surrounding water. And red are warm currents, which means that they're warmer than surrounding waters. They may have different speeds, but the one thing is that the system is rather stable. So it is unvariable, or should be rather unvariable. It should remain in balance. And quite a lot depends on this balance, as we'll see. But in general, currents account for about 40% of global heat transport. And also, this transport is much slower than the transport provided by winds, by the atmosphere. So they're slowly but surely they transport about 40% of the heat. So as you can see, they are a very important, significant contributor to the climate system. But why does water move? Why isn't the ocean this monotonous bowl of soup that we could actually expect? So there's influence of sunlight to start with. So we have many forces, maybe let's start with many forces that may cause this movement. And these forces being wind, tides, differences in water density, and also the rotation of Earth. maybe the rotation of Earth is not a root cause of the movement, but it does shape the movement and it influences the movement. Other factors are also affecting the way the system looks like, and this map that I showed you before looks like. So coastline, ocean floor topography, because also ocean floor isn't completely flat. It's just like the land floor. It's like land. It has its own topography, its own mountains, its own valleys. Of course, they're not exactly the same as on land, but it's definitely not flat and boring. So all that affects the movement of water. What does it mean that it affects it? Well, it can slow it down, accelerate it, change its direction, and so on. So in general, we have the influence of sunlight. Heating with solar energy causes the water to expand, right? So because the water has larger or higher temperature, it has larger volume. The same amount of water has larger volume with higher temperature. So if the polar regions receive not that much heat, and the regions near equator receive a lot of heat, that means that the water level of the ocean, of the world ocean, is higher near the equator than, for example, at mid latitudes. And the difference may seem not that significant, like about 8 centimeters. The difference between the ocean level near the equator and in mid latitudes. So if we have difference of levels, it results in a very small, very slight slope. So the water tends to run down the slope, just like the river on land. And also the flow is usually from east to west. So we have this influence of temperature that causes one type of movement, like from the slope. We have also influence of the wind, more precisely atmospheric circulation. So the wind is blowing on the surface of the ocean and pushes the water to move, affects the water the way that it just pushes it to move. And the friction between the wind and the water surface of the ocean pushes the water to move, and also makes it move along the course of the wind. So this is another force, and there is also the difference in water density, and water density has much to do with water salinity, not only but mainly with the salinity in the oceans. So differences in water density affect the mobility of ocean currents. So high salinity water is denser, of course, than low salinity water. Also, the cold water is denser than warm water. These are the two rules that are very important to remember. So more saline water and cold water are in general heavier, so they tend to sink. And lighter water, we might say, tend to rise. So these are the main primary forces, we might say, that in general cause the water to move. I also mentioned that the rotation of Earth around its axis also affects the movement, and it does, and it's so-called Coriolis effect, Coriolis force. So it's a phenomenon that causes the ocean currents, for example, to turn clockwise on the northern hemisphere and counterclockwise on the southern hemisphere. Clockwise, which means right, counterclockwise, which means left, on two different hemispheres. But why is it so? So when a body moves in a rotating frame of reference, and water is this body, but it can be also a boat or a plane. This is when this Coriolis effect phenomenon occurs. So it's like the object cannot move fast enough because of the Earth rotation. Don't want to go into the very huge detail, but in general, the interesting consequences, for example, that is very tangible for us, that if someone went to the top of the Eiffel Tower and dropped something, a body, like a person's body, but an object, it would fall 6.5 centimeters east from the point it was dropped from. So if you stand right on the top, it will go like this. It will fall 6.45 meters east. This is the eastern direction, and it will fall like that. And the Eiffel Tower is, well, it's rather high. It's like 273 meters high, but it's still not that high, not as high as the mountains. So this is also the effect of Coriolis effect. It's like the Earth was rotating all the time because it's rotating all the time. So the object fell like that. You remember, we're in Paris. The Eiffel Tower is, of course, in Paris, so we're in the northern hemisphere. And in the southern hemisphere, the effect would be opposite, so it would go west. So finally, if we know the primary forces that cause the water to move, we can focus on types and of ocean currents in general. So I would say the most important division, maybe even more important than cold currents and warm currents that we already mentioned, those red ones, which are warm, and blue ones on the map. This is how we mark the cold currents. I would say the division, according to where the currents form, but also what forms them exactly, is even more significant. So we have surface currents, surface circulation, and deep water currents, deep circulation. So surface currents, of course, they happen near the surface, but it's not like it's that near to the surface. It's even the surface may be, this layer may be even up to or down to 400 meters of the ocean. But it's only still about 10% of all water in the ocean. So the deep water currents, which are below 400 meters, constitute about 90% of the water. And surface currents are mainly formed by wind. So the wind causes friction, we already saw that, and as it moves over water. So the speed will be the greatest here. Very much near the surface, it's falling if we go down. And surface currents can travel long distances. Also, this Coriolis force that we talked about briefly plays a role in the movement, and it also deflects them, helping to create this rather circular pattern of surface currents. Then we have deep sea currents, deep circulation, and the force, the main driving force, is a difference in water density, which is also controlled, as we already know, by two factors: temperature and salinity, because once again, cold water is heavier, warm water is lighter. More saline water is heavier. Less saline, fresher water, we would say, is lighter. So we have those two factors, and In Greek, we have temperature known as thermo and salinity as halin. This process is therefore called thermohaline circulation. So as you can see, they have different location and different role and different genesis, those two types of ocean currents. And the thermohaline circulation, those deep water circulation, is the most important thing, or one of the most important things in the whole climate system. So you can see here those pumping stations. So those pumping stations play many different roles. First of all, they bring oxygen, but also this is where so-called deep water formation takes place. So again, polar regions, Earth polar regions, where the water is very, very cold. This is where sea ice is formed. So the water freezes. And once the water freezes, the fact is that it leaves all that it was in the water behind. I mean, all the salt. So the salt is left behind, and if you lick, please don't do that. If you ever lick the sea ice, you will see it's fresh, it is sweet. It's not salty. So if we take the water away, it forms sea ice, and then we leave a lot of salt. That means that the remaining water became very, very dense, became saltier, and also it was very, very cold because it was cold enough for the sea ice to form. So the density increases and the water begins to sink because it's so heavy. And this is the point of this deep water formation, as you can see here on the map. So the surface water goes down and it's replaced by new surface water. This is the pump. It's like sucking in this surface water because there can be no void. If the water goes down, some water needs to replace it. So eventually, this surface water, new surface water that replaced the original one, we might say, it also gets cold, and it also gets salty, and it's getting dense enough to drown, to sink, rather. So this process, this ongoing process, it's going on right now, initiates deep sea currents, driving this whole system, and this whole system is called a global conveyor belt. And the global conveyor belt is a system on a global scale. It moves around the world, it moves water around the world, but it's not only water that is being transported. It's like rather a mean of transport. With water, lots of nutrients and also carbon dioxide are transported. And this global conveyor belt is known as the main engine for the planet. So those polar regions, especially in the north, are very, very important. If something goes wrong in these regions here and also here, but mainly here, there's a problem. There's a problem with global transport of heat, of nutrients, of carbon dioxide. Like I said, it's very important to the balance of Earth. So the start is around here, it's Norwegian Sea, and the warm water from the Gulf Stream heats the atmosphere in the cold northern latitudes first. But if it heats the atmosphere, it means it's losing heat. And this loss of heat to the atmosphere keeps the water cooler and makes it cooler, and it gets denser. And as we already know, the process is sinking to the bottom of the ocean. And then it's being pushed by new water that arrives from the south, and it's going south as well. And it heads south along this Western Atlantic basin. So the current is also recharged as it travels along the Arctic. It picks up new, cold, salty, dense water. And then the main current is divided into two parts, one of which flows north into the Indian Ocean, and the other goes to the Western Pacific here. Both branches, you might say, of the current then heat up because it's very, very hot in here. So they heat up here or here in the Pacific Ocean or the Indian Ocean, and they then travel north. They go together, they travel north, and then they look back south and west, and here and here. This is here, this is what happens here, and this is what happens here, and they go back to the north. So this is where the cycle begins from the start, and it's rather slow, and it is estimated that each cubic meter of water takes around 1,000 years to complete the journey. So to come back here, say cubic meter of a drop of water. So it all depends on the main engine here, but also reviving the engine on the way. Why is it important? I already mentioned the transport of heat and of nutrients. So the system carries a lot. It also carries floating organisms such as plankton, larval fish, eggs, jellyfish, and populations may disperse, or sometimes it's even necessary for them to complete their life cycle, like in the case of eels or salmons. Also, these movements enable fertilization, which is often external fertilization. And of course, it provides oxygen, provides nutrients. Also, it removes some waste or impurities, but it can be a good thing or a bad thing. It not only removes the pollution or impurities, but can also cause the pollution to spread and to be brought far, far away from the original source, for example, of the catastrophe. And the heat transport, which is shaping the weather and consequently the climate as well. There are lots and lots of currents, and it's impossible to recognize and know them all. But the Gulf Stream is one of the strongest ocean currents in the world, and it is driven by the surface of wind patterns and differences in water density. So both factors play a role. And it influences the climate of the east coast of North America here, and also here, and the west coast of Europe. It makes east of North America and west of Europe warmer than it should normally be, but we're used to it being warmer. So it's very, very important. If it slows down significantly, it might mean very, very unpleasant consequences for inhabitants of those regions, because the climate there would become much less favorable. So again, what is the relation between ocean currents and climate change? The climate change may cause the disruption of this mechanism of global conveyor belt based on thermohaline circulation. It might weaken Gulf Stream because there would be not enough engine to give it power. Other effects that you may have heard about, the El Nino effect, El Nino and La Nina effect, which are often bringing catastrophic events. If there is slower transfer, there might also be slower carbon fixation. That means the uptake of carbon dioxide. And of course, if the ocean currents play such a huge role in transport also of living organisms, that it would mean any disruption in this system would cause the disruptions in the cycles of plankton, or disruption of all the food webs, and consequently also fishery, which is an industry that brings a lot of income to many people. As I mentioned, there are so many ocean currents that it would be impossible to know all of them. But this is in general, the scheme of all that. So again, we have red, which are warm, and blue, which are cold. For example, we have Peru current, Canary current, Benguela current, which are all blue, that means they're cold, and Gulf Stream, Brazil current, or Kuroshio current, which are warm current. That means that they're warmer than the surrounding water. This is a very interesting story about how incidents or even accidents can be used in the benefit of science, even if it seems a little bizarre. So this is a very famous story related to ocean currents and how we study them. Also, it happened in 1992, in January, on January the 10th. There was a storm in North Pacific. And yeah, in the North Pacific, there was a storm, and the storm washed away some containers, like 12 containers from the deck of the vessel, which is called a Laurel, and one of those 12 containers contained 29,000 rubber ducks. Actually, they were like floating toys, rubber toys, and some of them were ducks, and they were manufactured in China for the American company. They looked exactly like that. They were yellow rubber ducks. And it turned out they started living their own lives. And that means they were traveling thousands of nautical miles on their own completely. So the way that they would travel, it was like they were traveling on their own because they had some sort of engine. The only engine they were using were ocean currents. And it contributed to studying how they work. So they scattered around the world. Some, like 2/3, swam south here and landed on the shores of Indonesia, of South Australia, South America, but some of them, 10,000 of them, headed north, and they were settling on shores of Alaska, and sometimes they were crossing the Bering Strait. Some were stuck in the Arctic ice for years, and for example, some reached the shores of Great Britain and Ireland. And there was a record-breaking duck that reached Greenland. So the researchers were trying to predict correctly which direction the toys washed off the deck would go. And so they appealed to people to help them with the research. It was a sort of, I'd say, a semi-citizen science project. So even they paid people like $100 for each toy found in a place when it was predicted it should ship. I'm not sure they were probably marked in some way that did not allow people to cheat and just buy a regular yellow rubber duck and present it as this duck found on a beach. So this is one interesting story, and it shows that sometimes we learn more about nature, disrupting nature, unfortunately, but also thanks to chance and to fortune. Thank you very much.
Watch other recordings from webinars on our YouTube channel, youtube.com/EduArctic. EduArctic 2. From polar research to scientific passion, innovative nature education in Poland and Norway receives a grant of 240,000 euros received from Iceland, Liechtenstein and Norway under EEA funds.